Hello dear students, in this video I'll continue with the revision for CBSE board exam, and in this video we'll have a recap of the concepts from the topic differentiation and its applications from chapter 3A of CBSE Handbook. So we are aware of the standard results of differentiation. So these are the derivatives of standard functions. Derivative of x raised to n is n into x raised to n minus 1. Derivative of e raised to x is e raised to x. And then derivative of a constant is 0. Then derivative of a raised to x, it is equal to a raised to x into log a. And derivative of log x is 1 by x. Next we have the basic rules of differentiation. Derivative of k into a function of x, it is k into derivative of f of x. And next we have the derivative of sum of two functions or difference of two functions. Derivative of f of x plus or minus g of x, it is equal to derivative of f of x plus or minus derivative of g of x. And next we have the product rule. That is derivative of f of x into g of x. It is the derivative of the first function f of x into the second function g of x plus first function f of x into derivative of the second function g of x. And next we have the quotient rule. That is derivative of f of x upon g of x. It is given by the denominator has got g of x the whole square. Then we keep the denominator and differentiate the numerator. So it is derivative of f of x into g of x, then minus, we keep the numerator that is f of x and differentiate the denominator into derivative of g of x. And next we have differentiation of implicit functions. If we are able to write y as a function of x, then such functions are called explicit functions. So here we can find the derivative of y as f prime of x. On the other hand, if we have a function of this type, say x cube plus y cube minus 9xy equal to 0, here such functions are called implicit functions because we have a function of the form f of x comma y equal to 0. So such functions are called implicit functions, and we have to find the differentiation of such implicit functions. And now we'll see the examples from the CBSE handbook. If y equal to f of x is a real function, then find the derivative of the following with respect to x. The first one is we have to find the derivative of y square. So derivative of y square, it is 2y dy by dx. So we have to use chain rule to differentiate this. First we have to differentiate y square and then we have to differentiate y. So it is 2y dy by dx. The next subdivision is x cube into y raised to y raised to 5. So derivative of x cube into y raised to 5, we have to use product rule. So it is derivative of the first function into the second function plus first function into derivative of the second function. So this is equal to 3x square into y raised to 5 plus x cube is there. Here derivative of y raised to 5 is 5y raised to 4 into dy by dx. So this is the derivative of this function. And next we have the next subdivision, log of xy square. Now derivative of log of xy square, again we have to use chain rule first. So it is 1 by xy square into derivative of xy square. So here 1 by xy square is common, it can be kept outside. Now we have to use product rule to differentiate this. So this is 1 by xy square into derivative of x is 1 into y square plus x into derivative of y square is 2y dy by dx. So if we take this xy square inside the bracket, we get 1 by x plus 2 by y dy by dx. So this is the derivative of log of xy square. Next we have the fourth subdivision, x square upon 1 plus e raised to xy. So here we have to find the derivative using quotient rule. So this is derivative of d by dx of x square upon 1 plus e raised to xy. It is equal to, denominator we have 1 plus e raised to xy the whole square. Then we have to keep the denominator and differentiate the numerator. Derivative of x square is 2x minus x square into, we have to differentiate the denominator. So it is derivative of 1 plus e raised to xy is e raised to xy into, we have to use chain rule to differentiate 1 plus e raised to xy. So it is e raised to xy into, here we have to differentiate xy. So it is y plus x dy by dx. So this is equal to 2x plus e raised to xy into, now let us collect all terms with e raised to xy. So it is 2x minus x square y minus x cube dy by dx. The whole thing divided by 1 plus e raised to xy the whole square. So this is the derivative of x square by 1 plus e raised to xy. And next we have find dy by dx when x cube plus y cube equal to xy. So let us differentiate both sides with respect to x. We get 3x square plus 3y square dy by dx. Right hand side we use product rule to differentiate. So it is y plus x dy by dx. So let us collect all terms with dy by dx on one side. Dy by dx into 3y square minus x, it is equal to y minus 3x square. So from this we get dy by dx as y minus 3x square upon 3y square minus x. So this is dy by dx. Next we have if x raised to m into y raised to m equal to x plus y the whole raised to m, then show that dy by dx equal to y by x. So let us take log on both sides. Log of x raised to m into y raised to n. It is equal to log of x plus y the whole raised to m plus n. So this is log x raised to m plus log y raised to n. So this is m log x plus n log y. This is equal to m plus n into log of x plus y. Now let us differentiate both sides with respect to x. So we get m by x plus n by y dy by dx equal to m plus n upon x plus y. Here we have to use chain rule. So it is 1 by x plus y into derivative of x plus y. So it is 1 plus dy by dx. So let us collect all terms with dy by dx on one side. Dy by dx into n by y minus of m plus n upon x plus y. So here this is m plus n upon x plus y plus dy by dx into this term. So here we have dy by dx into n by y minus m plus n by x plus y. This is equal to m plus n by x plus y minus m by x. So dy by dx into nx plus ny minus my minus ny upon y into x plus y, taking LCM, equal to mx plus nx minus mx minus my upon x into x plus y. So here x plus y and x plus y will get cancelled. Here plus ny minus ny will go and plus mx minus mx will go. So we get dy by dx as nx minus my by y. This is equal to nx minus my by x. So these two will again get cancelled. So from this we get dy by dx equal to y by x. So this is what we have to show here, dy by dx equal to y by x. Hence proved. Next we have second and higher order derivatives. So let us take, let f of x be a differentiable function of x, then the derivative of f prime of x with respect to x, which is given by d by dx of dy by dx. That is, f prime of x is nothing but it is derivative of f of x, or it is dy by dx. So d by dx of dy by dx given by d square y by dx square equal to y double prime or f double prime of x. It is called the second order derivative of y or f of x. And next we have derivative of f double prime of x with respect to x. It is derivative of d square y by dx square. This is equal to d3y by dx3. And this is called the third order derivative of y or f of x. Similarly, we can find the higher order derivatives of y equal to f of x, and the nth order derivative is written as dny upon dxn equal to yn equal to fn of x. So this is with respect to second and higher order derivatives. Next we have differentiation of parametric functions. Sometimes the functions x and y will be written as function of another variable t. So if we have x is equal to f of t and y is equal to g of t. If we want to differentiate such functions, then such a differentiation is called differentiation of parametric function. So here x is a function of another parameter t and y is a function of t. So here we can find dy by dx as dy by dt upon dx by dt. Similarly, we can find d square y by dx square as d by dx of dy by dx, or it is d by dt of dy by dx into dt by dx. Now this is nothing but d by dt of dy by dx upon dx by dt. So this is how we can find higher order derivatives of parametric functions. And next we have some functions given in the form f of x the whole raised to g of x. If we want to find the derivative of such functions, then the derivative which we find, it is called logarithmic differentiation. So while doing problems, we can understand this better. Our next example, find dy by dx if x equal to at square and y equal to 2at. So we just now saw differentiation of parametric functions. So we have dy by dx as dy by dt upon dx by dt. So first we have to find. So here we can differentiate x and y with respect to t. Dx by dt, it is equal to derivative of at square with respect to t. So it is 2at, and dy by dt, it is equal to 2a. So dy by dx equal to dy by dt upon dx by dt. So this is 2a upon 2at, or it is equal to 1 by t. So this is dy by dx. Next we have find dy by dx at t equal to 1 if x equal to 1 minus t upon 1 plus t and xy equal to 2t cube. So here again differentiating with respect to t, we get dx by dt as, here we have to use quotient rule. So denominator square, then keep the denominator, differentiate the numerator, minus keep the numerator, differentiate the denominator. So this is minus 1 minus t minus 1 plus t upon 1 plus t the whole square. This is minus 2 by 1 plus t the whole square. Here there is a printing mistake. It is only y equal to 2t cube. Because in the solution they have solved using y equal to 2t cube. So dy by dt, it will be 6t square. So we have dy by dx as dy by dt upon dx by dt. Dy by dt is 6t square upon dx by dt is minus 2 upon 1 plus t the whole square. So from this we get dy by dx as minus 3t square into 1 plus t the whole square. Now we need to find dy by dx at t equal to 1. Dy by dx at t equal to 1. It is equal to minus 3 into 1 square, 1 plus t the whole square, into 1 plus 1 the whole square. So this is minus 3 into 2 square is 4, which is minus 12. So dy by dx at t equal to 1 is minus 12. Next we have the next question where we have to use logarithmic differentiation. We have to differentiate the following with respect to x. First subdivision is y is equal to x e raised to x. So first let us take log on both sides of the equation. We get log y equal to x log x. Now differentiating both sides with respect to x. We get 1 by y dy by dx equal to, we have to use product rule, so it is log x plus x into 1 by x. So from this we get dy by dx as y into log x plus 1, or we can substitute for y dy by dx, it is equal to x raised to x into log x plus 1. So this is dy by dx. Next question, y equal to x raised to y. So again let us take log on both sides. So we get log y equal to y log x. Now let us differentiate both sides with respect to x. So it is 1 by y dy by dx. Again we have to use the product rule. Dy by dx into log x plus y into derivative of log x, 1 by x. So let us collect all terms with dy by dx on one side. So dy by dx into 1 by y minus log x equal to y by x. So this implies dy by dx, taking LCM, 1 minus y log x upon y equal to y by x. Let us cross multiply and simplify. So we get dy by dx as y square upon x into 1 minus y log x. So this is the differentiation of y equal to x raised to y. Next question, if x raised to y plus y raised to x equal to a raised to b, then find dy by dx. So here let us take Let u equal to x raised to y and v equal to y raised to x. Then x raised to y plus y raised to x equal to a raised to b implies u plus v equal to a raised to b. Now let us differentiate both sides with respect to x. We get du by dx plus dv by dx. It is equal to 0. Now let us find du by dx and dv by dx from here. U equal to x raised to y implies log u equal to y log x. Let us differentiate both sides with respect to x. So we get 1 by u du by dx equal to dy by dx log x plus y by x. This is 1 by u du by dx. So from this we get du by dx equal to u into dy by dx log x plus y by x. But u we have taken as x raised to y. So this is equal to x raised to y into this term. Now v equal to y raised to x implies log v equal to x log y. Now let us differentiate both sides with respect to x. So we get 1 by v dv by dx equal to, here we have to use product rule. So it is log y plus x by y dy by dx. So here we get dv by dx as v into this term. V is y raised to x. So from this we get dv by dx equal to y raised to x into log y plus x by y dy by dx. Now let us take this as equation 1, du by dx as equation 2 and dv by dx as 3. Now substituting 2 and 3 in 1, we get x raised to y dy by dx log x plus y by x plus y raised to x log y x by y dy by dx equal to 0. So this is x raised to y log x dy by dx plus here x raised to y into y by x will be x raised to y minus 1 into y. X raised to y minus 1 into y plus y raised to x log y plus here y raised to x into x by y will be y raised to x minus 1 into x. So it is x into y raised to x minus 1 dy by dx equal to 0. So here we can collect all terms with dy by dx on one side and take the other terms to the other side. So we get dy by dx into x raised to y log x plus x into y raised to x minus 1 equal to minus of x raised to y minus 1 into y plus y raised to x log y. So from this we get dy by dx as minus of x raised to y minus 1 into y plus y raised to x log y upon x raised to y into log x plus x into y raised to x minus 1. So this is dy by dx. When we have x raised to y plus y raised to x is equal to a raised to b. Now let us continue. Find dy by dx for the following functions. The first one, y equal to x. So here dy by dx equal to 1. So d square y by dx square, 1 is a constant, so derivative of 1 is 0. Here dy by dx will be derivative of log x, which is 1 by x. Then d square y by dx square, it is derivative of 1 by x. So derivative of 1 by x is minus 1 by x square. Next we have y equal to root of x square minus 1. So here dy by dx equal to, here x square minus 1 is x square minus 1 the whole raised to half. So derivative of x square minus 1 the whole raised to half is half into x square minus 1 the whole raised to half minus 1, which is minus half, into derivative of x square minus 1 using chain rule. So into 2x. So this is x by root of x square minus 1. This is dy by dx. Now we need to find d square y by dx square. D square y by dx square, we have to use quotient rule. So root of x square minus 1 the whole square. Here we have to keep the denominator and differentiate the numerator, which is 1, minus x into, we have to differentiate the denominator, root of x square minus 1. So root of x square minus 1, it is nothing but x by root of x square minus 1 into x by root of x square minus 1. So d square y by dx square, this is equal to, denominator will be x square minus 1 into root of x square minus 1 minus x square by root of x square minus 1. Now let us take LCM. LCM is x square minus 1. LCM is root of x square minus 1. So here root of x square minus 1 into root of x square minus 1 is x square minus 1. Then minus x square upon x square minus 1 into root of x square minus 1, that is x square minus 1 the whole raised to half. So plus x square minus x square will get cancelled. This is minus 1 by, here x square minus 1 the whole raised to 1 into x square minus 1 the whole raised to half. So it is x square minus 1 the whole raised to 1 plus half, which is 3 by 2. X square minus 1 the whole raised to 3 by 2. This is d square y by dx square. Moving on, if x is equal to t square by 1 plus t and y equal to t by 1 plus t, find y2. Here y2 is nothing but it is d square y by dx square. So first let us differentiate with respect to t. So dx by dt, it is equal to, using quotient rule, denominator is 1 plus t square, keep the denominator, differentiate the numerator, minus, keep the numerator, differentiate the denominator. So here the numerator is 2t plus 2t square minus t square. So it is 2t plus t square. So this is 2t plus t square upon 1 plus t the whole square divided by 1 plus t the whole square. Now let us find dy by dt. So dy by dt, here y is t by 1 plus t. So this is 1 plus t the whole square. Keep the denominator, differentiate the numerator, minus, keep the numerator, differentiate the denominator. So this is 1 plus t minus t, so it is 1 by 1 plus t the whole square. And now dy by dx is dy by dt upon dx by dt. So it is 1 by 1 plus t the whole square upon 2t plus t square upon 1 plus t the whole square. So these two will go. Here we have 1 by 2t plus t square. This is dy by dx. Now d square y by dx square, it is d by dx of dy by dx, or it is d by dt of dy by dx into dt by dx. So this is d by dt of dy by dx upon dx by dt. So it is derivative of 1 by 2t plus t square with respect to t upon dx by dt. Now let us differentiate this. So using chain rule, it is minus 1 by 2t plus t square the whole square into 2 plus 2t upon dx by dt is this 2t plus t square upon 1 plus t the whole square. So this is minus of 2 is common, let us take it outside, into 1 plus t upon 2t plus t square the whole square into 1 plus t the whole square upon 2t plus t square. So here it is minus 2 into 1 plus t the whole cube upon 2t plus t square the whole cube. Here inside this bracket 1t is common, can be taken outside, so it will be t cube. So this is minus 2 into 1 plus t the whole cube upon t cube into 2 plus t the whole cube. This is d square y by dx square. So this is how we have to find d square y by dx square for the parametric functions. Next we have the cost and revenue function. The cost function, it is given by if v of x is the variable cost of producing x units and if k is the fixed cost, then the cost function is given by the sum of variable cost and the fixed cost. Next we have revenue function. If R is the total revenue of a company which receives by selling x units of quantity at a price p per unit, then the revenue function is given by R of x is equal to p into x. And next we have marginal cost and marginal revenue. So marginal cost and marginal revenue, they are nothing but they are the instantaneous rate of change of cost and revenue with respect to output. That is the rate of change of cost, that is the cost function, and R of x, the revenue function with respect to the production output, which is x. So marginal cost is the rate of change of cost function with respect to x. So it is given by dc by dx, and marginal revenue is the revenue function. It is dr by dx. It is the rate of change of revenue function with respect to x. So it is dr by dx. So here if a company wants to maximize the profit, then it will produce up to the point where marginal cost equals the marginal revenue. Beyond that point, the cost of producing one additional unit, it will exceed the revenue generated. So if an economy is a profit maximizing one, then it has to produce up to the level where marginal cost equal to the marginal revenue. So we have to remember this concept. One question in the sample paper was asked based on this concept. And now we will move on to examples. A company produces x units in a year and the variable cost is v of x is equal to x square minus 2x. Also the company spends a fixed cost of rupees 15,000 on commissions and rent. Then find the total cost function, that is the first subdivision. So first let us find the total cost function, and next we have if p is the price per unit given by p equal to 5 minus x, then find the revenue function. So we know how to find total cost function and how to find the revenue function. Here variable cost is given as v of x is equal to x square minus 2x, and fixed cost is given as rupees 15,000. So the total cost function c of x, it is given by v of x plus k. It is x square minus 2x plus 15,000. So this is the total cost function. The total revenue function r of x, it is given by p into x. Here p is given by 5 minus x. So this is 5 minus x into x. It is 5x minus x square. So the revenue function is given by 5x minus x square. Now we have the next topic, which is derivative as rate of change of quantities. Now we know dy by dx is nothing but it is the rate or the instantaneous rate of change of y with respect to x. So we have some applications of this derivative as rate of change of quantities. Here is an example. A boy is blowing air into a spherical balloon and thus the radius r of the balloon is changing. Then find the rate of change of surface area of the balloon with respect to radius r. Also find the rate of change of surface area when r equal to 2 centimeter. So we know what is the formula for surface area. So with that we can find the rate of change of surface area with respect to r. That is, we have to find dA by dr. And then we can find the rate of change of surface area when r is 2 centimeter. So let us take, let area of balloon be A at radius r. Then A is given by, it is equal to 4 pi r square. So rate of change of surface area of the balloon with respect to the radius, it is given by dA by dr. So it is the derivative of 4 pi r square with respect to r. So this is equal to 8 pi r. Now we need to find the rate of change of surface area when r equal to 2 centimeter. So this is 8 pi into 2. So this is 16 pi centimeter square per centimeter. So this is also centimeter square per centimeter. So these are the answers. Next we have related rates. In related rate problems, the quantities change with respect to time. You may be given rate of change of one variable with respect to time and rate of change of other variable has to be found with respect to time. So here we are familiar with parametric functions when x is given as a function of t and y is also given as a function of t. Then we find dy by dx as dy by dt upon dx by dt. So if we want to find dy by dt, we can find dy by dt as dy by dx into dx by dt. So these are few things that we have to remember in questions with related rates. So here find the rate of change of volume of a sphere with respect to its surface area when the radius is 5 centimeter. So here we have to find the rate of change of volume with respect to surface area. So we have to find dV by ds of a sphere when the radius is 5 centimeter. So here for radius r, volume v and surface area s of a sphere, it is given by v is 4 by 3 pi r cube and s is 4 pi r square. So here we know that v and s are both functions of r. So we will use the chain rule to find derivative of v with respect to s. So for that first let us find dv by dr and ds by dr. dv by dr will be 4 by 3 into 3 pi r square. That is the derivative of this with respect to r. So this is 4 pi r square and ds by dr, it is 8 pi r. Now we need to have dv by ds. dv by ds is dv by dr upon ds by dr. So this is 4 pi r square upon 8 pi r. This is equal to r by 2. So dv by ds, it is equal to r by 2. We need to find the rate of change of volume with respect to surface area when radius is 5. So dv by ds when r equal to 5 meter, it is 5 by 2. So it is 2.5 meter cube per meter square. So this is dv by ds. Moving on to the next question. A cylindrical vessel of radius 0.5 meter is filled with oil at the rate of 0.25 pi meter cube per minute. Find the rate at which the surface of the oil is increasing. So here we can see that when the radius of the cylindrical vessel is 0.5 meter, the rate at which the volume of the oil is increasing, it is given. It is 0.25 pi meter cube per minute. So using this, we can find the rate at which the height is increasing. This is nothing but the rate at which the surface of the oil is increasing. So the rate at which the volume rises is the rate of change of height of the oil in the vessel rises with respect to time. So if we take r as the radius, h as the height, v as the volume of the oil at any time t, we have p equal to pi r square h. This is the volume of the cylinder. Now r is given as 0.5 meter. So v is equal to, it is pi into r is half the whole square into h. So this is pi by 4 h. So we got volume as pi by 4 into h. Now let us differentiate v with respect to t. dv by dt. This is equal to pi by 4 into dh by dt. But we already have this dv by dt. It is 0.25 pi meter cube per minute. This implies 0.25 pi. It is equal to pi by 4 into dh by dt. So from this we get 1 equal to dh by dt or dh by dt equal to 1 meter per minute. So this is the rate at which the surface of the oil is rising. Next question. A boy of height 1 meter is walking towards a lamppost of height 5 meters at the rate of 0.5 meter per second. Then find the rate at which the length of the shadow of the boy is decreasing. So here we can see that the height of the boy, it is 1 meter and the height of the lamppost is 5 meters and the boy is walking towards the lamppost. So here if we consider this PQ as the lamppost of height 5 meter and if we consider the position of the boy at any time t at r, rs is the height of the boy which is 1 meter. So here we take the distance between the lamppost and the boy as x and the length of the shadow of the boy as y. So here we take let rt equal to y be the length of the shadow of the boy when he is x meters away from the lamppost at any time t. So here since the boy is walking towards the lamppost at a speed of 0.5 meters per second, we have this as negative. dx by dt, it is negative 0.5 meters per second. Since the boy is walking towards the post, x is decreasing, so here we have a negative sign. Now if we consider triangle PQT and RST, we can see that triangle PQT similar to triangle RST. So their corresponding sides are proportional. Since triangle PQT similar to triangle RST, PQ by RS equal to PT by RT. So 5 by 1, this is equal to x plus y by y. So from this we get 5y equal to x plus y or 4y equal to x or y is equal to x by 4. Now let us differentiate with respect to t. Differentiating with respect to t. dy by dt equal to 1 by 4 into dx by dt. Now since we already have dx by dt as negative 0.5, dy by dt, it is minus 0.5 by 4 or 0.5 is half. So this is minus 1 by 8 meters per second. So the shadow of the boy is decreasing at the rate of 1 by 8 meters per second. So it is decreasing. So we need not write another negative symbol here. So it is decreasing at the rate of 1 by 8 meters per second. dy by dt, it is equal to minus 1 by 8 meters per second. A toy manufacturing firm assesses its variable cost to be x times the sum of 30 and x, where x is the number of toys produced. Also, the cost incurred on storage is rupees 1500. Find the total cost function and the marginal cost when 20 toys are produced. So here we can see that the variable cost is given as x into 30 plus x and the storage cost is 1500. This is the fixed cost. We have to find the total cost function and the marginal cost when 20 toys are produced. So here the total cost function c of x, it is given by c of x is equal to variable cost plus fixed cost. So c of x is equal to variable cost is x into 30 plus x plus 1500. So this is 30x plus x square plus 1500. This is c of x. The marginal cost is given by, marginal cost is the derivative of total cost. So it is derivative of 30x plus x square plus 1500. So it is 30 plus 2x. So this is marginal cost. Now marginal cost of producing 20 toys, it is equal to marginal cost at x is equal to 20. So it is 30 plus 2 into 20. So this is 30 plus 40, which is 70. So the marginal cost of producing 20 toys, it is rupees 70. Next question, the price per unit of a commodity produced by a company is given by P equal to 30 minus X and X is the quantity demanded. Find the revenue function R, marginal revenue when 5 commodities are in demand. So here P is given, we need to find the revenue function which is given by P into X and then we can find the marginal revenue. Revenue function R of X is given by R is equal to P into X. So it is 30 minus 2x into x or R of x is equal to 30x minus 2x square. Marginal revenue is given by derivative of the revenue function. So this is 30 minus 4x. This is marginal revenue. And now marginal revenue of producing 5 commodities. It is dr of x by dx at x is equal to 5. So this is 30 minus 4 into 5. It is 30 minus 20, which is 10. So marginal revenue when 5 commodities are in demand, it is rupees 10. So this is marginal revenue. Next we have slope of tangent and normal to a curve and equation of tangent and normal to a curve. So let us take, let y equal to f of x be a real function. So if we have this curve y equal to f of x, then the slope or gradient of a non-vertical tangent at a point A, x0, y0. It is given by the derivative of this function dy by dx at x0 comma y0. So that is the slope. And next, if y equal to f of x is a real function, then the normal to the curve at the point A x0 y0, that is x0 f of x0. It is a line which is perpendicular to the tangent at the given point of the curve. So this is the normal at point A. The slope of this normal, it is given by minus 1 by slope of this tangent. So it is given by minus 1 by dy by dx at this point A x0 comma y0. And next we have equation of tangent and normal. Now equation of a line which is passing through x1 y1 and having a slope m, it is given by y minus y1 equal to m into x minus x1. So equation of tangent to a curve at the point A x0 y0 is given by y minus y0 into slope of the tangent. So here slope is m, slope of the tangent we just now saw, it is dy by dx at x0 comma y0 into x minus x0. Similarly, equation of normal to the curve at this point A x0 y0. It is y minus y0 equal to slope of the normal. This is slope of the normal. Minus 1 by dy by dx at x0 y0 into x minus x0. So this is with respect to slope of tangent and normal and equation of tangent and normal to a curve. Now let us continue with the examples. Find the slope of tangent and normal at the point 2, 6 to the curve y equal to x cube minus x. So here we have y equal to x cube minus x. So that dy by dx, it is equal to 3x square minus 1. So here slope of the tangent at the point 2, 6, it is given by dy by dx at 2, 6. So we do not have any y here. So it is 3 into 2 square minus 1. It is 12 minus 1, which is 11. And here slope of the normal at the point 2, 6, it is given by minus 1 by dy by dx at 2, 6. So this is minus 1 by 11. So this is the slope of the tangent and this is the slope of the normal at this point 2, 6 to the curve y equal to x cube minus x. Next question, find the equation of the tangent and normal to the curve x raised to 2 by 3 plus y raised to 2 by 3 equal to 2 at the point 1, 1. So let us differentiate the equation with respect to x. We have to differentiate this with respect to x. So x raised to 2 by 3, if we differentiate, we get 2 by 3 into x raised to 2 by 3 minus 1, which is minus 1 by 3, plus here y raised to 2 by 3, if we differentiate, we get 2 by 3 into y raised to 2 by 3 minus 1, which is minus 1 by 3 into dy by dx. This is equal to 0. So from this we get dy by dx. It is equal to minus 2 by 3 into x raised to minus 1 by 3 by 2 by 3 into y raised to minus 1 by 3. Or this is minus y raised to 1 by 3 upon x raised to 1 by 3. So equation of the tangent at this point 1, 1, it is given by y minus 1 equal to dy by dx at 1, 1 into x minus 1. So this implies y minus 1 equal to dy by dx at 1, 1, it is minus 1 by 1, which is minus 1. dy by dx at 1, 1 equal to minus 1 equal to minus of x minus 1. So this implies y equal to minus x plus 2. So this is the equation of the tangent. And next equation of the normal, it is given by y minus y1, it is 1 equal to minus 1 by dy by dx at 1 comma 1 into x minus x1, which is 1. So here dy by dx at 1 comma 1, it is minus 1. So from this we get y minus 1 equal to minus 1 by minus 1 into x minus 1, or y minus 1 equal to x minus 1. So from this we get y minus x is equal to 0. This is the equation of the normal, and this we can write it as x plus y minus 2 equal to 0. This is equation of the tangent. Next question, find the equation of the tangent and normal to the curve f of x is equal to e raised to x plus x square plus 1 at the point 0, 2 on it. So first let us differentiate with respect to x to find the slope. F dash of x is e raised to x plus 2x. So slope of tangent, it is given by f dash of 0 equal to f dash of 0 equal to e raised to 0 plus 2 into 0. This is 1. And slope of normal, it is minus 1 by f dash of 0, which is minus 1. Now equation of the tangent, it is given by y minus 2 equal to f dash of 0 is 1 into x minus 0, or x minus y plus 2 equal to 0. This is the equation of the tangent. And equation of the normal, it is given by y minus 2 equal to minus 1 into x minus 0, or from this we get x plus y minus 2 equal to 0. So this is the equation of the tangent, this is the equation of the normal. Next example, find the equation of the tangent to the curve x square plus 3y minus 3 equal to 0, which is parallel to the line y equal to 4x minus 5. So here we need to find the equation of the tangent to this curve, which is parallel to this line. So if the tangent is parallel to this line, then the slope of the tangent and slope of the curve will be, slope of the tangent and slope of the line will be equal. So slope of the tangent is 4. So first let us differentiate this with respect to x. Differentiating with respect to x, we get 2x plus 3 dy by dx equal to 0, or from this we get dy by dx equal to minus 2 by 3 x. So slope of tangent equal to, it is equal to 4, since tangent is parallel to this line. Since tangent is parallel to y equal to 4x minus 5, slope of the tangent is equal to 4. So from this we get dy by dx equal to 4 implies 4 equal to minus 2 by 3 x. So from this we get x as minus 6. So we got one point as minus 6. The other point we can substitute in the curve and we can find the other coordinate y. Minus 6 the whole square plus 3y minus 3 equal to 0 implies, this is 36 minus 3, 33, 3y equal to minus 33, or y equal to minus 11. So the equation of the tangent, so we got the point as minus 6 comma minus 1. Equation of the tangent at minus 6 comma minus 11 is given by y minus y naught. So it is y plus 11 equal to m into, here slope is 4. So 4 into x plus 6. So from this we get y plus 11 equal to 4x plus 24, or we get 4x minus y then plus 13 equal to 0. So this is the equation of the tangent. Next we have find the equation of the tangent to the curve y equal to x cube minus 1 into x minus 2 at the point where the curve cuts the x-axis. So here we need to find the equation of the tangent at those points where this curve cuts the x-axis. So if the curve cuts the x-axis, then the y-coordinate is 0. So here putting y equal to 0 in the equation of the curve to get the points where it cuts the x-axis, we get 0 equal to x cube minus 1 into x minus 2. So from this we get 0 equal to x minus 1 into x square plus x plus 1 into x minus 2. So from this we get x as 1 comma 2. You cannot equate this to 0 x square plus x plus 1. If we equate, we will get a complex number for x. Therefore, the point of intersection of the curve with the x-axis are 1 comma 0 and 2 comma 0. Now let us find the slope of the tangent. So for that we have to differentiate this equation with respect to x. dy by dx equal to, let us use product rule, 3x square into x minus 2 plus x cube minus 1 into 1. So this is 3x cube minus 6x square plus x cube minus 1, which is 4x cube minus 6x square minus 1. Now let us find the slope of the tangent at the 2 points. dy by dx at 1 comma 0. So it is 4 minus 6 minus 1 minus 3. Then dy by dx at 2 comma 0. It is 32 minus 24 minus 1, which is 7. 2 comma 0, it is 4 into 2 cube minus 6 into 2 square minus 1. So this is 32 minus 24 minus 1, which is 7. Now the equation of the tangents, they are given by equation of tangent at 1 comma 0 and the other one is equation of tangent at 2 comma 0. So at 1 comma 0 we have y minus 0 equal to dy by dx at 1 comma 0, which is minus 3 into x minus 1, or we have 3x plus y minus 3 equal to 0. The other equation is y minus 0 equal to 7 into x minus 2, or we have 7x minus y minus 14 equal to 0. So these are the two equations of the tangent at the points where the curve cuts the x-axis. Next question, find the equation of the tangents to the curve 3x square minus y square equal to 0, which passes through the point 4 by 3 comma 0. So here if we see this point 4 by 3 comma 0, it does not lie on this curve. So we have to find the equation of the tangents to this curve which passes through this point. So let us assume the tangent touches the curve at the point h comma k. So if the tangent touches the curve at the point h comma k, we get 3h square minus k square equal to 8. Let us mark this as equal to 1. Now let us differentiate the equation of the curve with respect to x. We get 6x minus 2y dy by dx equal to 0. Or from this we get dy by dx as minus 6x upon minus 2y. So it is 3x by y. Now since we assume that the tangent touches the curve at the point h comma k, dy by dx at h comma k, it is equal to 3h by k. And now the equation of the tangent through this point, it is given by equation of tangent at h comma k, it is given by y minus k equal to 3h by k into x minus h. Now since the tangent passes through this point 4 by 3 comma 0, since tangent passes through this point 4 by 3 comma 0, we have 0 comma k equal to 3h by k into 4 by 3 minus h. So from this we get minus k square equal to 3h into 4 minus 3h upon 3. So from this we get k square equal to 3h square minus 4h. So let us take this as equation 2. Now from here let us substitute k square as 3h square minus 8. This implies 3h square minus 8 equal to 3h square minus 4h. This is from 1. So from this we get h is equal to 2. So if we put h equal to 2 in this equation, we will get the two values of k and we will get the points at which the tangent touches the curve. So from 1, 3 into 2 square minus k square equal to 8. This implies here 12 minus 8 is 4 equal to k square, or we get k equal to plus or minus 2. This implies the points are 2 comma 2 and 2 comma minus 2. So these are the 2 points. Now equation of the tangents we can find. Equation of tangents are first we have y minus 2 equal to dy by dx at 2 comma 2 into x minus 2. So here dy by dx at this point we have 3 into 2 by 2, it is 3. This implies y minus 2 equal to 3 into x minus 2, or we have 3x minus y minus 4 equal to 0. Then the other equation is y plus 2 equal to dy by dx at 2 comma minus 2 into x minus 2. So this implies y plus 2 equal to, here dy by dx at this point we have 2 comma minus 2, 3 into minus 2 by 3 into 2 by minus 2, so it is minus 3. Minus 3 into x minus 2. So this implies we have 3x plus y plus 2 minus 6. It is minus 4 equal to 0. So these are the two equations of the tangents. Moving on with the next question, prove that x by a the whole raised to n plus y by b the whole raised to n equal to 2. It touches a straight line x by a plus y by b equal to 2 for all n belongs to n at the point a comma b. So we have to prove that this curve, it touches this straight line x by a plus y by b equal to at this point a comma b. So first let us simplify this. X by a the whole raised to n plus y by b the whole raised to n equal to 2 implies x raised to n into b raised to n plus y raised to n into a raised to n upon a raised to n b raised to n equal to 2, taking LCM. So we get x raised to n b raised to n plus y raised to n a raised to n equal to 2a raised to n b raised to n. Now let us differentiate this equation with respect to x. So we get n into b raised to n into x raised to n minus 1 plus n into a raised to n into y raised to n minus 1 into dy by dx equal to 0. So from this we get dy by dx equal to minus n into b raised to n into x raised to n minus 1 upon n into a raised to n into y raised to n minus 1. And now let us find dy by dx at this point a comma b. Dy by dx at a comma b, it is equal to minus b raised to n into a raised to n minus 1 upon a raised to n into b raised to n minus 1. So this is nothing but b by a minus b by a. It is b raised to n minus n plus 1 upon a raised to n minus n plus 1. So this is, it is minus b raised to 1 upon a raised to 1, which is b by a. So the equation of the tangent at this point a comma b, it is given by y minus b equal to dy by dx at a comma b into x minus a. So y minus b equal to minus b by a into x minus a. So here let us bring this b to this side. So here we will get y by b minus 1. Y by b minus 1 equal to here minus x by a plus 1. Here minus x by a, here minus of minus plus a by a is 1. So from this we get x by a plus y by b equal to 1 plus 1, which is 2. So here we need to prove that this curve touches this straight line x by a plus y by b equal to 2 for all n at this point. So we have proved that the equation of the tangent to this curve at this point a comma b, it is x by a plus y by b equal to 2 irrespective of the value of n. Next example, find the points on the curve y equal to 4x cube minus 2x raised to 5 at which the tangent passes through the origin. So here we need to find all those points on the curve y equal to 4x cube minus 2x raised to 5 where the tangent passes through 0, 0. So let us take, let h comma k be any such point on this curve. Now since h comma k is any such point, then we can put x as h and y as k. This implies k equal to 4h cube minus 2h raised to 5. Let us take this as equation 1. Now let us differentiate this equation of this curve with respect to x. We get dy by dx equal to 12x square minus 10x raised to 4. Now since we have taken h comma k as the point, now dy by dx at h comma k, it is given by 12h square minus 10h raised to 4. So the equation of the tangent which is passing through the origin, it is given by y minus 0 equal to slope of the tangent. It is this 12h square minus 10h raised to 4 into x minus 0. Again, since the tangent, it passes through the point h comma k, so here we can put y as k and x as h. As h comma k lies on the tangent, we have k equal to 12h square minus 10h raised to 4 into h, or we get k as 12h cube minus 10h raised to 5. So here let us take this as 2. From 1 and 2, the left hand sides are equal, so we can equate the right hand side. 4h cube minus 2h raised to 5 equal to 12h cube minus 10h raised to 5. So from this we get 8h raised to 5 minus 8h cube equal to 0, or we get 8h cube into h square minus 1 equal to 0. So we get h as 0 and plus or minus 1. So we got the coordinates for h, that is 0, plus 1 and minus 1. We can find the coordinates for k by substituting the x coordinate 0, 1 and minus 1 in this curve. So when x equal to 0, y equal to 0, x equal to 1, y equal to 4 minus 2 equal to 2, and when x equal to minus 1, y equal to minus 4 plus 2, which is minus 2. Therefore, the points are 0, 0, then 1, 2 and minus 1, minus 2. So these are the points on this curve y equal to 4x cube minus 2x raised to 5, at which the tangent passes through the origin. Next we have increasing and decreasing functions. So we call a real function y equal to f of x an increasing function on the open interval a comma b if the value of f increases as x increases, or if the value of x decreases as x decreases. So here we can see that x1 is less than x2. Here x1 is less than x2 and f of x1. This is f of x1. This is less than f of x2. So we call this curve f of x is equal to 0.2 into x minus 2 the whole square. This is the curve. This is an increasing function. So an analytical condition for a function to be increasing on a comma b given by x1 less than x2 implies f of x1 less than f of x2 for all x1 comma x2 belongs to this open interval a comma b, or x1 greater than x2 implies f of x1 greater than f of x2 for all x1 comma x2 belongs to the open interval a comma b. So this is with respect to increasing function. The next function we have is called decreasing function. So we call a real function y equal to f of x a decreasing function on the open interval a comma b if the value of f decreases as x increases, or if the value of f increases as x decreases. So here the graph of f of x, it falls from the left to right. So here we can see that x1 is less than x2. Here x1 is less than x2. On the other hand, this is f of x1. F of x1 is greater than f of x2. So here we can see that when x1 is less than x2, here x1 is less than x2, but f of x1, it is greater than f of x2. So this is a decreasing function. So this function minus 2.5 into 0.5x minus 2.1 the whole square plus 8, where x varies from 4 to 7.5. This is a decreasing function. So here we have an analytical condition for a function to be decreasing on a comma b. So x1 less than x2 implies f of x1 greater than f of x2 for all x1 x2 belong to this open interval a comma b, or x1 greater than x2 implies f of x1 less than x2 for all x1 x2 belong to the open interval a comma b. If one of these conditions is satisfied, then we call such a function a decreasing function. Those functions which are either increasing or decreasing functions are called monotonic functions. So here a function which is either increasing or decreasing on its domain, an open interval, it is termed as a monotonic function. Then we can see that a function, it may be defined to be increasing or decreasing in any of the following interval which is represented as I. So it can be either increasing or decreasing on any of these intervals. The term upward sloping, it is also used for increasing function. So If a function is upward sloping, then such a function is an increasing function. The term downward sloping is also sometimes used for decreasing function. So if we have a downward sloping curve, then the function is a decreasing function. And now we will see the example question on increasing function, decreasing function. Show that f of x equal to x square is an increasing function on open interval 0, comma infinity and decreasing function on minus infinity, comma 0. So let us do each subdivision one by one. Here we have to show that x square, it is increasing on this interval and it is decreasing on the interval minus infinity, comma 0. So for the first subdivision, let us take any 2 points x1, x2 which belongs to the open interval 0, comma infinity such that x1 is less than x2. Now let us multiply here both sides of the inequality with x1. So x1 into x1, it is less than x1 into x2, which implies x1 square less than x1 into x2. Since x1 and x2 they are positive numbers. Again, let us multiply both sides of the inequality with x2. So we get x1 into x2 less than x2 into x2 implies x1 into x2, it is less than x2 square. So here from these two inequalities, we can say that hence x1 square less than x2 square, which means f of x1 less than f of x2. So we started with x1 less than x2 and we got f of x1 less than f of x2. The meaning is that f of x is an increasing function on this interval, open interval 0, comma infinity. Therefore, x1 less than x2 implies f of x1 less than f of x2 implies f is increasing on open interval 0, comma infinity. So this is the conclusion. Now let us move on to the second subdivision. In the second subdivision, again let us take 2 points x1, x2 which belongs to this interval minus infinity, comma 0 such that x1 less than x2. Now here we can see that x1 and x2 are negative numbers. So if we multiply both sides by x1, the inequality changes. x1 into x1, it will be greater than x1 into x2, implies x1 square greater than x1 into x2. Since x1 and x2 are negative numbers. Also, now let us multiply both sides with x2, x1 into x2. Again it will be greater than x2 into x2. This implies x1, x2 greater than x2 square. So from these two we can see that hence x1 square greater than x2 square, which implies f of x1 greater than f of x2. So we started with x1 less than x2, but we got f of x1 greater than f of x2. Hence f is decreasing on this interval minus infinity, comma 0. Therefore, x1 less than x2 implies f of x1 greater than f of x2. So this implies f is decreasing on open interval minus infinity, comma 0. So here we can see that f of x equal to x square, it is an increasing function on this interval 0, comma infinity, and it is a decreasing function on the interval minus infinity, comma 0. Now say for example, if we are asked to find whether f of x equal to x square, it is decreasing on the interval minus infinity comma infinity. If we have a situation like this, say for example, now here we can see that f of x equal to x square, it is decreasing on minus infinity comma 0 and it is increasing on 0 comma infinity. So if we consider the interval minus infinity comma infinity, f of x is neither increasing nor decreasing. So here let us note this point, f of x is decreasing on minus infinity comma 0 and increasing on 0 comma infinity. Therefore, we say that f of x is neither increasing nor decreasing on the open interval minus infinity comma infinity. Now let us move on with derivative conditions for a monotonic function. So we have a derivative test for finding whether a function is increasing or decreasing. A real function y equal to f of x is an increasing function on open interval a comma b if f dash of x greater than 0 for all x belongs to open interval a comma b, and a real function y equal to f of x is a decreasing function on open interval a comma b if f dash of x is less than 0 for all x belongs to a comma b. So if this condition is satisfied, then we say f of x is an increasing function, and if f dash of x is 0 for all x belong to the open interval a comma b, then we say f of x is a decreasing function. And next we have the term known as the critical points. Now critical points are nothing but it is an interior point of the domain of a function f where f is 0 or undefined. So two conditions that has to be satisfied for a critical point is that it has to be an interior point in the domain of the function f, and at this critical point f dash is 0, that is the derivative of f is 0 at this point, or it should not be defined, it is undefined at this point. So here we use this word because at this point there is an abrupt change in the behavior of the graph, that is the graph will come straight, it changes the direction, or it will go like this and it changes direction, or it keeps increasing, stops at a point, and then again it will increase. So when there is an abrupt change in the behavior of the graph of the function, then we call such points as critical points. A function f of x is defined in an interval I and C is an interior point of I. If f of x is continuous at x is equal to c and f dash of c equal to 0, then c is called a critical point. If f of x is continuous at c and f dash of c is not defined also, then c is it is considered as a critical point. And if c is a point of discontinuity, then again c is a critical point, and here also f dash of c is not defined. Next we have what is known as stationary point. The stationary point is the point where the derivative of the function is 0. So here it is a point where the curve is momentarily at rest and then it will take a smooth turn, or it becomes a point of inflection. So here again stationary points are necessarily the interior points of the domain of the function. So these are with respect to stationary points. Now we will move on with the examples. Find the critical points of the following function. So we have seen that at the critical points f dash of x is 0. So we can equate f dash of x to 0 and solve for x to find the critical points. The first subdivision f of x is equal to 12 into x raised to 4 by 3 minus 6 into x raised to 1 by 3 on the closed interval minus 1 comma 1. So here we need to find the critical points. So let us find f dash of x. Now f dash of x is equal to 12 into 4 by 3 into x raised to 4 by 3 minus 1. So it is 1 by 3 minus 6 into 1 by 3 into x raised to 1 by 3 minus 1. So it is minus 2 by 3. This is equal to 0. Implies f dash of x is equal to 16x raised to 1 by 3 minus 2 upon x raised to 2 by 3. So here the LCM is x raised to 2 by 3. So 16 into x raised to 1 by 3, if we multiply and divide by x raised to 2 by 3, we get this as 16 into x raised to 1 by 3 plus 2 by 3, which is 3 by 3 upon x raised to 2 by 3. So this is 16x upon x raised to 2 by 3. So here we will have 16x minus 2 upon x raised to 2 by 3. This is equal to 0. This implies 16x minus 2 equal to 0, which implies x is equal to 2 by 16 or it is equal to 1 by 8. So the critical point is x is equal to 1 by 8, and here we can see that when x is equal to 0, f dash of x is not defined and x is equal to 0, since f dash of 0 is not defined. So these two are the critical points. So these two are the critical points. Next question, f of x is equal to x raised to 4 by 4 minus 2x cube plus 11 by 2 x square minus 6x. So we have to find the critical points for this function. First let us find f dash of x. F dash of x is 1 by 4 into 4x cube minus 2 into 3x square plus 11 by 2 into 2x minus 6. So this is x cube minus 6x square plus 11x minus 6. This is equal to 0. So to find the first point, here let us substitute x as 1 and check. When we substitute x is equal to 1, f dash of 1 is equal to 1 minus 6 plus 11 minus 6 equal to 0. So this implies x minus 1 is a root of this equation. So f dash of x is equal to x minus 1 into, and now to find the other factors we can perform synthetic division. So for that, first let us write the coefficients of all these. X cube is 1, x square is minus 6, x is 11, constant is minus 6. Here we have x minus 1. So here we have 1, bring this 1 here. This 1 into 1 is 1. We have to add these two, minus 6 plus 1 minus 5. Next 1 into minus 5 minus 5. Here again we have to add these two. 11 minus 5 is 6. Then 1 into 6 is 6. So here minus 6 plus 6, 0. So this is the coefficient of x square, this is coefficient of x, and this is the constant. Into x square minus 5x plus 6. Here this is the remainder. When we divide this polynomial with x minus 1, when we divide this polynomial with x minus 1, we will get the quotient x square minus 5x plus 6 and remainder as 0. This is equal to 0. This implies f dash of x equal to x minus 1 into, now this is a quadratic equation in x. The factors of 6 are 2 and 3, that is minus 2 minus 3. So here we will have x minus 2 into x minus 3 as the roots, equal to 0. Therefore, x equal to 1, 2 and 3 are the critical points. So these are the critical points. Next question, using derivatives, check whether the following functions are monotonic. The first one is f of x equal to x square. on the open interval 0, infinity. So we have to check whether these functions are monotonic or not. So we just now saw if a function is increasing, then f dash of x should be more than 0, and if it is decreasing, then f dash of x should be less than 0. So here f dash of x equal to 2x and 2x is greater than 0 for all x belongs to the open interval 0, infinity. Therefore, the function is increasing and it is monotonic. That is, the function is increasing on the open interval 0, infinity, and hence it is a monotonic function. Next we have the second subdivision, f of x is equal to x square on the open interval minus infinity, 0. So the second subdivision, f dash of x is equal to 2x, and here we can see that 2x is less than 0 for all x belongs to open interval minus infinity, 0. So here the function is decreasing on the open interval minus infinity, 0. So it is a monotonic function. So if a function is either increasing in its domain or if it is decreasing on its domain, then it is called a monotonic function. Let us move on. The next subdivision, f of x is equal to x square on minus infinity, infinity. So here we can see that f of x is x square. So f dash of x equal to 2x. At the critical points, f dash of x equal to 0 implies x is equal to 0. So x is equal to 0 is a critical point. So we have to divide this interval minus infinity to infinity as minus infinity, 0 and 0, infinity. So we can see that f dash of x equal to 2x. It is less than 0 for all x belongs to minus infinity, 0, and f dash of x equal to 2x. It is greater than 0 for all x belongs to 0, infinity. So here it is decreasing on this interval and it is increasing on this interval. So on the interval minus infinity, infinity, it is neither decreasing nor increasing. We conclude that the function is neither increasing nor decreasing on the open interval minus infinity, infinity. Hence the function is not monotonic on this given interval. And now we have the next question, f of x is equal to x raised to 1 by 3. So let us find f dash of x. F dash of x is equal to 1 by 3 into x raised to 1 by 3 minus 1, which is minus 2 by 3. So it is 1 by 3 into x raised to 2 by 3. So here we can see that x is equal to 0 is a critical point since f dash of x is not defined at x is equal to 0. X is equal to 0 is a critical point since f dash of x is not defined at x is equal to 0. So here we can divide the entire interval minus infinity to infinity into minus infinity to 0 and 0 to infinity. So first let us consider the interval minus infinity to 0. F dash of x is 1 by 3 into x raised to 2 by 3 is x raised to 1 by 3 the whole square. Now this is more than 0 for all x belongs to minus infinity, 0. Again f dash of x equal to 1 by 3 into x raised to 1 by 3 the whole square. This is also more than 0 for all x belong to 0, infinity. So here we can see that f of x is an increasing function on its domain and hence it is a monotonic function. So it is increasing from minus infinity to 0 and 0 to infinity. So it is a monotonic function. Next question, find the intervals in which the function f of x is equal to x raised to 4 by 4 minus 2x cube plus 11 by 2 x square minus 6x is increasing and decreasing. The same question was given in the sample paper for 3 marks. So here we have to find the intervals in which this function, it is increasing and decreasing. So first we have to find the critical points and then we can find the intervals. So first let us find f dash of x. F dash of x is equal to 1 by 4 into 4x cube minus 2 into 3x square plus 11 by 2 into 2x minus 6. For the same question we have already found the critical points, but still let me find it again. So this is x cube minus 6x square plus 11x minus 6. This is equal to 0. So if we consider x as 1, then f dash of 1 is 1 minus 6 plus 11 minus 6 equal to 0. This implies x minus 1 is a factor. So f dash of x is equal to x minus 1 into. Now let us divide this polynomial with x minus 1 using synthetic division. The coefficients are 1 minus 6, 11 minus 6. Here we have 1. We have to bring this 1 here. 1 into 1, 1 minus 6 plus 1 minus 5. 1 into minus 5 minus 5. 11 minus 5 is 6. Then 1 into 6 is 6 minus 6 plus 6 is 0. So this is x minus 1 into x square minus 5x plus 6 equal to 0. So from this we get x minus 1 into x square minus 5x plus 6 is x minus 2 into x minus 3 equal to 0. So x equal to 1, 2 and 3. These are the critical points. So we can divide the entire interval from minus infinity to 1, then 1 to 2, then 2 to 3 and then 3 to infinity. So let us draw a table like this so that we can find the sign of f dash of x and to conclude whether it is increasing or decreasing. So the various intervals are minus infinity comma 1, open interval, then open 1 comma 2, then open interval 2 comma 3 and open interval 3 comma infinity. So if we consider the interval minus infinity comma 1, if we substitute any point in this interval, say 0. So if we substitute x as 0 here, this is negative, this is negative, this is also negative. So overall the sign of f dash of x will be negative. Negative into negative into negative. This is positive into negative is negative. So f dash of x is less than 0. So the conclusion is f is decreasing on this interval. So here f is decreasing. Next, moving on to the next interval 1 comma 2. Now let us substitute any point in this interval 1 comma 2 and check. Say let us substitute 1.5. So here if we substitute 1.5, this will be positive. Then here 1.5 minus 2, this is negative. 1.5 minus 3, this is negative. So negative into negative is positive. So f dash of x is more than 0. Therefore, f is increasing on this interval. And next we have the next interval 2 comma 3. Now let us substitute any point, say 2.5 and check. 2.5 minus 1, it is positive. Then 2.5 minus 2 is again positive. And here 2.5 minus 3, it is negative. So here again f dash of x will be less than 0. So the conclusion is f is decreasing on this interval. And finally we have the last interval 3 comma infinity. If we substitute any point, say 4 and check. Here all these will be positive. 4 minus 1 positive, 4 minus 2 positive, 4 minus 3 positive. So here f dash of x is more than 0. So f is increasing on this interval. So we can finally see that f is increasing on the intervals open interval 1 comma 2 union open interval 3 comma infinity, and it is decreasing on the intervals open interval minus infinity comma 1 union open interval 2 comma 3. So here finding the critical points carries 1 mark, then finding the intervals in which it is increasing carries 1 mark, and finding the intervals in which it is decreasing carries 1 mark. So a total of 3 marks for this question. Let us move on with the examples. Next question. The cost function c of x of a commodity is given as c of x is equal to 2x into x plus 3 upon x plus 2 plus 2. Prove that the marginal cost falls as the output x increases. So we have to prove that marginal cost function, it is a decreasing function. So we have to prove that marginal cost falls as x increases. That is, we have to prove that derivative of the marginal cost, it is less than 0. So here the cost function is given. It is 2x into x plus 3 upon x plus 2. Let us write it as 2 into x square plus 3x upon x plus 2 plus 2. Now let us find c dash of x. C dash of x is 2 into, we have to use the quotient rule, so denominator whole square, then keep the denominator, differentiate the numerator, minus keep the numerator, differentiate the denominator into 1, plus derivative of a constant is 0. So this is 2 into 2x square plus 4x plus 3x is 7x plus 6 minus x square minus 3x upon x plus 2 the whole square. So this is 2 into x square plus 4x plus 6 upon x plus 2 the whole square. Here let us complete the squares in this part. So here we have x square plus 4x. I am adding and subtracting 4. So that we get this as 2 into x plus 2 the whole square plus 2 upon x plus 2 the whole square. Now this c dash of x, it is nothing but it is the marginal cost. This if we simplify, we get it as equal to 2 into 1 plus 2 by x plus 2 the whole square. This implies marginal cost is equal to 2 into 1 plus 2 by x plus 2 the whole square. Now we have to show that marginal cost falls as the output x increases. So let us find the derivative of marginal cost. So here derivative of marginal cost, it is 2 into, already 1 2 is there, derivative of 1 by x plus 2 the whole square will be minus 2 by x plus 2 the whole cube. So this is minus 8 by x plus 2 the whole cube, which is less than 0 as x increases. So here hence the marginal cost falls continuously as the output increases. So this is what we have to prove, and we have proved. Next, moving on to maxima and minima. Let y equal to f of x be a real function defined on a set D. Then we say f of c is the absolute minimum value of f of x on D if f of x is greater than or equal to f of c. That is, all values when substituted for x in f of x, it should be more than or equal to f of c. In that case, we say f of c is the absolute minimum value of f of x. Similarly, f of c is the absolute maximum value of f of x on D if f of x is less than or equal to f of c for all x belongs to D. So, f is said to have absolute extremum value in its domain if there exists a point C in this domain such that f of c is either the absolute maximum value or the absolute minimum value of the function f in this domain, and the number f of c, it is called the absolute extremum value of f in its domain, and c is called the point of extremum. So these are some of the terms which should be remembered: absolute extremum value, point of extremum, all these things. Now we have the next example. Find the maximum, that is absolute maximum and absolute minimum value of the following functions. The first subdivision, f of x is equal to mod x plus 3. First subdivision. Now we know mod x, it is greater than or equal to 0. So this implies mod x plus 3, it is greater than or equal to 0 plus 3. Mod x plus 3 is nothing but it is the given function f of x. F of x is greater than or equal to 3. So we have seen that if f of x is greater than or equal to f of c, then f of c is the absolute minimum value of f of x. So the absolute minimum value of f of x, it is 3. Hence minimum of f of x is equal to 3, but here f of x is greater than or equal to 3, so it has no maximum value. And next we have f of x is equal to 9x square plus 12x plus 2. Second question subdivision, consider 9x square plus 12x plus 2. So this is 9x square is 3x the whole square plus 2 into 3x into 2. I am adding and subtracting 4. So this is nothing but 3x plus 2 the whole square minus 2. Now we can see that 3x plus 2 the whole square is greater than or equal to 0. So 3x plus 2 the whole square minus 2 greater than or equal to 0 minus 2, which is minus 2. So this 3x plus 2 the whole square minus 2, it is nothing but it is f of x. This implies f of x is greater than or equal to minus 2. So here again, hence the minimum value of f of x is equal to minus 2. But f of x has no maximum value. Next we have f of x is equal to 2x plus 5, where x belongs to the open interval minus 2 comma minus 4. So since x belongs to the open interval minus 2 comma minus 4, we have minus 2 less than x less than 4. Let us multiply by 2. So minus 4 less than 2x less than 8. Let us add 5. Minus 4 plus 5 less than 2x plus 5 less than 8 plus 5. So from this we get 1 less than 2x plus 5 is nothing but f of x. Less than f of x less than 13. Since we are having an open interval, so here we get 1 less than f of x less than 13. So here f of x, it has got no maximum value or no minimum value. So f of x has no maximum or minimum value. If at all this interval was closed interval, then we will get equal to symbol here, 1 less than or equal to f of x less than or equal to 13. In that case, f of x will have maximum and minimum values. But here in this case, f of x has no maximum or minimum value. Now let us continue with the next topic, which is local maxima and local minima. Say for example, if we have a continuous function f of x which is defined on the open interval a comma b. say this is the function given by f of x. So here we can see that it is increasing up to point A and then it starts decreasing. Again it is increasing, then starts decreasing, again it is increasing and then starts decreasing. So these points A, C, E, all these are called the points of local maxima. These points A, C, E, they are called the points of local maxima. And the value of f of x at these points, they are called local maximum values. Similarly, B, D, these points are called points of local minima. If we consider a point of local maxima, here in the left neighborhood of A, the function is increasing, and to the right neighborhood of A, the function is decreasing. Then such a point is called a point of local maxima. Similarly, if we consider this point B, here in the left neighborhood of B, the function is decreasing, and in the right neighborhood of B, the function is increasing. Then such a point is called a point of local minima. So here is the definition. Let f be a real valued function and let C be an interior point in the domain of f. Then f is said to have a local maximum value at C if there exists a positive real number h such that f of c greater than f of x for all x belongs to c minus h comma c plus h minus the point C. Then in this case, C is called a point of local maximum and f of c is the local maximum value. And next we have f is said to have a local minimum value at C if there exists a positive real number h such that f of c less than f of x for all x belongs to open interval c minus h comma c plus h minus c, and c is called the point of local minimum and f of c is called a local minimum value. Now we have the first derivative test to find the point of local maxima and local minima. If f is a function defined on the open interval a comma b, and if f is continuous at a critical point C belongs to a comma b, then we call this point C as the point of local minimum if there exists h greater than 0 such that f dash of x is less than 0 for x belong to c minus h comma c, and f dash of x is greater than 0 for all x belong to c comma c minus h. So this is what I have mentioned already. So here if we consider a graph like this, if we consider this point here this is the point C, which is the point of local minima. Here we can see that f of x is decreasing in the left neighborhood of C and increasing in the right neighborhood of C. So it changes its sign from negative to positive as x increases to C, and f of C is a local minimum value of f of x. And next we have C as a point of local maximum if there exists h greater than 0 such that f dash of x is greater than 0 for all x belong to c minus h comma c, and f dash of x is less than 0 for all c comma c minus h. So at all these points, if we consider this point, it is a point of local maxima. So at all these points, that is in the nearest neighborhood of C, at all these points f dash of x is more than 0, and in the right neighborhood of C, here at the points from C to C plus h, f dash of x is less than 0, it is decreasing. Then in that case we call this point C as a point of local maximum. So here f of x is increasing in the left neighborhood of C and decreasing in the right neighborhood of C, or it changes its sign from positive to negative. So here it is positive and here it is negative as x increases through C. If f dash of x does not change sign as x increases to C, then C is neither a point of local maximum nor local minimum, and it is called a point of inflection. So the next question, find all points of local maxima and local minima and the local maximum, local minimum values of the function f of x equal to x raised to 4 minus 8x cube plus 22x square minus 24x plus 1. So we just now saw the first derivative test, how to find the points of local maxima and local minima. So using that test, let us find the points of local maxima and local minima for this function. So to find the local maxima, local minima, first let us find the critical points. So to find the critical points, we need to find f dash of x. F dash of x is 4x cube minus 24x square plus 44x minus 24. This is equal to 0 at the critical points. So this implies f dash of x is equal to 4 into x cube minus 6x square plus 11x minus 6 equal to 0. So here if we substitute x as 1, we already saw, then we will get f dash of 1 as equal to 0. So f dash of x is 4 into x minus 1 into, now let us divide this by x minus 1 using synthetic division. The coefficients are 1, minus 6, 11, minus 6. Here we have 1 into 1, 1, minus 6 plus 1, minus 5, minus 5 into 1, minus 5, 11 minus 5 is 6, 6 into 1, 6, minus 6 plus 6, 0. So it is x minus 1 into x square minus 5x plus 6. This is equal to 0, or it is 4 into x minus 1 into, here this is a quadratic equation in x, we have the factors as x minus 2 into x minus 3. This is equal to 0. Therefore, we get x is equal to 1, 2 and 3 as the critical points. So these are the critical points. So let me continue here. We got f of x as 4 into x minus 1 into x minus 2 into x minus 3 equal to 0. So the critical points are x is equal to 1, 2, 3. So let us find the sign of f of x. Sign of f dash of x on this number line. So the various intervals are minus infinity to 1, then 1 to 2, then 2 to 3 and 3 to infinity. From minus infinity to 1, if we substitute any point, say 0 and check, it is negative, negative, negative. So when we multiply all those, we get f dash of x is less than 0 on this interval. Next, if we consider any point from 1 to 2, say 1.5, here it is 1.5 minus 1 positive, here 1.5 minus 2 negative, 1.5 minus 3 negative, so negative into negative positive. Here f dash of x is more than 0. Next, if we consider any point, say 2.5, this is positive, this is positive, this is negative. So on this interval, f dash of x is less than 0. And on the interval 3 to infinity, f dash of x is more than 0. So first let us consider the point x equal to 1. So at x equal to 1, here we can see that in the left neighborhood of 1, f dash of x is less than 0. It means it is decreasing. The function is decreasing. If this is 1, here if we have x as 1, it is decreasing in the left neighborhood of 1 and then it starts increasing, because in the right neighborhood f dash of x is more than 0. F is decreasing in the left neighborhood of x is equal to 1 and f is increasing in the right neighborhood of x equal to 1. So f dash of x changes its sign from negative to positive as x increases through 1. So x is equal to 1 is a point of local minima, and the local minimum value is f of 1 is equal to, f of 1 is, we have to put x as 1 in f of x. So 1 minus 8 plus 22 minus 24 plus 1. This is equal to minus 8. And next let us consider the next point at x is equal to 2. So this is the point x is equal to 1. At x is equal to 2, we can see that to the left of x is equal to 2, f dash of x is more than 0. So here f dash of x is increasing and then it is decreasing. So at this point x is 2. So here x is equal to 2 is a point of local maxima. So at x is equal to 2, f is increasing in the left neighborhood and f is decreasing in the right neighborhood of x is equal to 2. Of x is equal to 2. So f dash of x changes its sign from positive to negative as it increases through 2. So x is equal to 2 is a point of local maximum, and the local maximum value is f of 2 equal to 2 raised to 4 is 16 minus 64 plus 22 into 4 88 minus 24 plus 1. So here f of 2 it is equal to minus 7. And next we have the next point, which is x is equal to 3. At x is equal to 3. So at this point x is equal to 3. Here to the left of 3, we can see that f dash of x is less than 0. The meaning is that the function is decreasing. So here the function is decreasing, and then to the right of 3 it is increasing. So at this point x is 3. So x is equal to 3 is again a point of local minima. F is decreasing in the left neighborhood of 3 and f is increasing in the right neighborhood of x is equal to 3. So here f dash of x, it changes its sign from negative to positive as x increases through 3. So x is equal to 3, it is a point of local minima, and the local minimum value is f of 3, it is 3 raised to 4 81, 18 to 27 216 plus 198 minus 72 plus 1. So this is equal to minus 8. So here the points of local minima are x is equal to 1 and x is equal to 3, and the point of local maxima is x is equal to 2. Now we have the second derivative test to find the points of local maxima and local minima. Let f be a function defined on the open interval a comma b, and let f be continuous at a critical point c belongs to a comma b. Then the point c is a point of local minimum if f dash of c is equal to 0 and f double dash of c is more than 0. That is f prime of c is, so first we have to find f dash of x equated to 0 and find the critical point. So c is a critical point, and we have to find f double dash of x and substitute c and check. If f double dash of c, if it is more than 0, then we say f of c is a local minimum value and c is a point of local minima. Next we have point c as the local maximum if f dash of c equal to 0 and f double dash of c is less than 0. And we say f of c, it is the local maximum value of f of x. Sometimes we will get a situation where f double dash of c is equal to 0. Then in that case, the second derivative test will fail and we have to apply only first derivative test to check whether c is the point of local maximum, local minimum, or whether it is a point of inflection. If f dash of x, if it does not change sign as x increases through c, then we call c as a point of inflection. Next question, use the second derivative test to find the local maxima and minima of f of x is equal to 4 by 3x cube plus 6x square plus 8x equal to 7. So here f of x is 4 by 3 x cube plus 6x square plus 8x plus 7. So at the critical points, f dash of x is equal to 0. So let us find f dash of x. So it is 4 by 3 into 3x square plus 12x plus 8 equal to 0. Or it is here 4 is common into x square plus 3x plus 2 equal to 0. So this implies x plus 2 into x plus 1 equal to 0, or x is equal to minus 1 comma minus 2 are the critical points. Now let us find f double dash of x. F double dash of x is, that is f, the second derivative of f of x. It is 4 into 2x minus 2x plus 3. Now let us check at each of these points whether this f double dash of x is more than 0 or less than 0. At x equal to minus 1, f double dash of minus 1, it is 4 into minus 2 plus 3. This is equal to 4, which is more than 0. So here we can see that for x equal to minus 1, we get f double dash of x, it is more than 0. So x equal to minus 1, it is a point of local minima. So x equal to minus 1 is a point of local minima, and the local minimum value, it is given by f of minus 1 equal to minus 4 by 3 plus 6 minus 8 plus 7. So this is 5 minus 4 by 3, which is 11 by 3. So f of minus 1 is 11 by 3. And now let us find f double dash of x at x is equal to minus 2. At x is equal to minus 2, f double dash of minus 2, it is equal to 4 into, here 2 minus 2 into minus 2, it is minus 4 plus 3. So this is equal to minus 4, which is less than 0. So we got f double dash of x at x is equal to minus 2 as less than 0. The meaning is that x is equal to minus 2, it is a point of local maxima. So x is equal to minus 2 is a point of local maxima, and the local maximum value is f of minus 2. It is equal to 4 by 3 into minus 2, the whole cube is minus 8, plus 6 into 4, 24, minus 16 plus 7. So this is equal to 15 minus 32 by 3, or it is 13 by 3. So the local maximum value is f of minus 2 equal to, it is 13 by 3. So this is how we have to go about using the second derivative test to find the point of local maxima, local minima, and the local minimum and the local maximum values. Next question, use the second derivative test to find the local maxima and minima of f of x is equal to x cube minus 3x square plus 3x plus 5, if any. So here first let us find f dash of x. F of x is x cube minus 3x square plus 3x plus 5. F dash of x will be 3x square minus 6x plus 3, or it is 3 into x square minus 2x plus 1. At the critical points, f dash of x equal to 0 implies x minus 1 the whole square equal to 0, or x is equal to 1. So here x is equal to 1 is a critical point. Now let us find f double dash of x. F double dash of x is 3 into 2x minus 2. So at x equal to 1, f double dash of 1 is 0. Since only when f double dash of x is less than 0 or more than 0, we can find the points of local maxima or local minima. Here we are getting it as equal to 0. So the second derivative test fails. So the second derivative test fails. So we have to use the first derivative test to find the point of local maxima and local minima. So if we consider the number line from minus infinity to infinity, we have one critical point which is 1. So here we can see that to the left of 1, that is in the left neighborhood of 1, f dash of x is 3 into x minus 1 the whole square. So in the left neighborhood of 1 it is positive, and in the right neighborhood of 1 also it is positive. In the left neighborhood of 1, of x is equal to 1, f dash of x is greater than 0, and in the right neighborhood of 1, f dash of x is again greater than 0. So if f dash of x does not change sign, then we call the point x is equal to 1 as a point of inflection. F dash of x does not change sign as x increases through 1. This means that x is equal to 1. It is a point of inflection. So here the graph will be something like this. It will keep on increasing. Next we have maximum and minimum values in a closed interval. So if y equal to f of x, if it is a real continuous function defined in a closed interval a comma b, then we have to use the following steps to find the maximum and minimum value. The first step is we have to find all the critical points by solving f dash of x equal to 0 in the open interval, and then if we are having x1, x2 up to etc. xn, that is n critical points, then we have to find n plus 2 values of the function. That is, we have to find the value of f of x. We have to find the value of f of x at these endpoints of the intervals a comma b, and at the n critical points that we are getting. And finally, the largest among f of a, f of x1, f of x2 up to etc., f of x and f of b, that is the absolute maximum value, and the least among this is the absolute minimum value of the function. So this is how we have to go about if a function is a real continuous function, if it is defined in a closed interval a comma b. So here is an example. Find the absolute maximum and absolute minimum value of the function f of x is equal to x cube minus 3 by 2 x square minus 18x plus 1 on closed interval minus 4 comma 6. So here the interval is closed. So we have to find the critical points first, and we have to find the value of x at the critical points and at minus 4 and 6. And then The highest among all those will be the absolute maximum value, and the least among all those will be the absolute minimum value. So here f dash of x is equal to 3x square minus 3 by 2 into 2x minus 18. This is equal to 0. This implies 3 into x square minus x minus 6 equal to 0. So 3 into x minus 3 into x plus 2 equal to 0. So x is equal to, the critical points are x is equal to minus 2 comma 3. So the critical points, it should lie in this interval, which belongs to the closed interval 4 comma 6. Therefore we have to find the value of f of x at minus 4, minus 2, 3 and 6. The values of f of x at minus 4, minus 2, 3, 6. So first let us find f of minus 4. It is minus 4 the whole cube minus 3 by 2 into minus 4 the whole square minus 18 into minus 4 plus 1 minus 64, then minus 24, then plus 72 plus 1. So this is equal to minus 15. Next we have f of minus 2. So f of minus 2, it is minus 8, minus 3 by 2 into 4, it is minus 6, then plus 36 plus 1. So this, when we simplify, it is 23. Next f of 3 cube is 27 minus 27 by 2 minus 54 plus 1. So this, when we simplify, we get it as minus 39.5. Next we have f of 6. f of 6 is 6 cube 216 and next minus 3 by 2 into 6 square minus 18 into 6 plus 1. This is equal to 55. So here we can see that among all these, the least is minus 39.5 and the highest is 55. So this is minimum and this is maximum. So the absolute minimum value of f of x is minus 39.5 and the absolute maximum value of f of x is 55. So these are the various concepts that we have to remember in differentiation and its applications. All these concepts are explained with examples from the CBSE Handbook. I hope this video was useful for you. If you have not subscribed to my channel, please subscribe. If you like this video, share it with your friends. Thank you for watching.